Good morning, everyone. Welcome to our tutorial of graph mining in recommender system advice 2021. I am Hongxu Chen, now working at the University of Technology, Sydney as a research fellow. My research interests are in graph mining and its applications. And together with me today, we have two PhD students, Ms. Yitong Li and Haoran Yang, will also cover some parts of this tutorial. The agenda of today's tutorial will cover three parts. First, I will introduce the general graph representation learning and its applications in recommender systems. Yitong will give a talk on graph-based explainable recommender systems. And lastly, Haoran will summarize the recent progress of the graph-trained trusted learning in recommender systems. I believe all these topics are quite hot with recent research trends, and we will try the best to keep these contents up to date. First, let us look at the first topic, graph representation learning and its application in recommender systems. Graph or networks are ubiquitous, which can be used for modeling and representing many kinds of real-world data, such as social network, information network, roles, user item behavior interactions, etc. The advantages of graph representation learning are that they are quite flexible to deposit any typed data and the complex interactions among them. Traditionally, networked data are usually represented as adjacency matrix, where each row and column represents an entity in a graph, and the values denote the weighted or binary links. However, in the era of big data, information networks grow rapidly at a very large scale, which makes the traditional adjacency matrix inefficient and expensive for computational purpose. To this end, graph representation learning has become a prevalent tool that tries to learn low-dimensional vector representations for vertices in a graph, such that the learned embedding vectors can effectively preserve network structures. Here is an illustration of how graph embedding works. And the input is a graph, while a mapping function, the method will output a d-dimensional feature representations, which also known as embeddings. The embeddings need to satisfy some predefined properties depending on particular embedding techniques. For example, two embedding vectors should be close in embedding space if the corresponding nodes are close in original graph. Graph embedding methods can be categorized into these three categories, which are early matrix factorization-based methods, random walk-based methods, and the recent graph neural networks. We will discuss these categories together with the recommender system in detail in the following chapters. Here is a link for the graph learning methods. Interested audience are encouraged to refer to this course, which is online available from Stanford University. When talking about recommender systems, normally we are talking about the interactions between users and items, and the data can be naturally modeled as bipartite graph, where various interactions can be made between two different sets of nodes, which are users and items. Meanwhile, with the content and the knowledge associated with the users and items, including, for example, friendship relations among users, item attributes associated with items, etc. All of those links and heterogeneous nodes can contribute to a bigger knowledge graph. Therefore, graphs are a basic representation for recommender systems. Okay, first, we are looking at the recommender system based on bipartite graph mining. In general, recommender system models based on bipartite graph embedding techniques they are for static user item interactions. Those methods are normally based on metric factorization and Bayesian analysis and deep learning methods. From an overview, the matrix factorization methods, which is a pioneer of bipartite graph embedding, provides a well extensibility as a probabilistic version of the matrix factorization methods. By setting regulation terms of models through prior knowledge, such as the fact that the error follows a Gaussian distribution, the Bayesian analysis method to some extent alleviate the non-convex optimization issue of the matrix factorization methods caused by the sparsity problem. With ability in efficiently learning and preserving nonlinear patterns in data, deep learning methods has been also very dominating in recent years. Here is a reference material showing that the recent development of bipartite modeling approach. Due to time limitation, we do not go to the details of all those techniques. Interested audience can be referred to the survey and the original papers for details. In short, the matrix factorization method is the most extensible one, succeeding various subsequent variants. However, the current focus has substituted the deep learning methods for the matrix factorization methods for the advantage in nonlinear pattern discovery and the parallel computing of the former is meeting the technique requirements of increasing complexity and the scale of the data for recommender systems. To model the recommender systems, general graph modeling approaches are still prevalent at the moment. The methods can be categorized into knowledge graph completion-based methods, such as the famous trans-family translation-based methods, including, for example, the trans-E, trans-R, trans-H, and trans-G, and so on. Apart from that, random walk-based approaches and deep learning-based approaches are also dominant in recent years. The translation family approach is originally designed for knowledge graph completion tasks. The translation-based methods model the basic elements, that is triplets, a head, relation, and a tail, denoting a head entity and a tail entity, which are linked with a particular type of link R. For example, trans-E models a relation R as a translation from the head entity H to tail entity T. Trans-H maps each pair of head and tail to multiple relational specific hyperplanes, distinguishing the diverse relationships between nodes. While trans-R maps the nodes and the relation separately into a node space and multiple different relation space corresponding to the diverse relation between head-tail pairs respectively. Apart from the methods related to knowledge graph modeling, existing works also model the node sequences generated by the passes or on the recommender graphs. Among them, the metapath is the representative effective method for semantic representation of complex relationships between two nodes. Metapath is a meta-level description of a path between two objects, and the different metapaths tell different semantics. The following example here tells a metapath representing co-author relationships by defining specific metapaths, author, paper, author from a citation network. To learn the embedding for the downstream recommender system, metapaths and other paths related like random walk generated passes over a graph can be fed into a encoding functions to obtain the embeddings of each particular node in the graph, which are inspired by advances in NLP, such as the word-to-vec methods. Researchers treat the passes like words in a sequence, in a sentence. By applying the skipgram model and negative sampling techniques, which could find the final node embeddings. This representative methods in this line include line, which is large information network embedding, random walk, deep walk, node to vec, metapath to vec, and BINE, bind. Most of the methods are based on the generated node sequences and the skipgram model, and which has been very successful and became very popular in recent years. So apart from that, deep learning methods are also widely used for graph mining. The methods include both dedicated graph neural networks and some methods derived from other purposes. For example, the graph convolutional neural networks are designed for convolutional operations directly on the graph, while methods like transformers can be used as well. As well if we treat the nodes passes as a sequences. Among all these methods, TNNs and the simplified version based on message passing and information aggregation are trendy techniques in the contemporary research fields. Here is a referenced summary of the recent development of general graph embedding methods. Apparently, all these methods, all these three categories of techniques can be applied in the recommendation, in the recommender systems, in which cases, those based on the metapath and deep learning are the broadcast ones. Relevant research in recent years has concentrated on taking into account the temporal information when embedding a general graph, and also on the preserving of the multiplicity of the heterogeneous information networks. And we will be discussing some of the key items in the following chapter. So above, we have briefly summarized the key methods for graph modeling based recommender system and the recent development. Here, there is an open problem about the embedding space for recommender system. Recently, hyperbolic space has been explored as a new latent space, and it has shown very impressive performance. It outperforms the Euclidean space in many domains, including natural language processing, link prediction, and node classification, as well as the top-end recommender systems. A key property of hyperbolic space is that it expands faster than the Euclidean space. Euclidean space expands polynomially, while the hyperbolic space expands exponentially. In other words, the data capacity of hyperbolic space is larger than Euclidean space. Another important property of hyperbolic is that it can preserve the hierarchies of the data, which is very common in many real-world data such as text or e-commerce networks and social networks. In general, complex networks. Although hyperbolic embedding are gaining great attention for recommender system nowadays, it is not clear under what circumstances the hyperbolic space should be considered. A critical analysis and guidance are missing in existing literature. As the current trendy topic of hyperbolic embeddings, practitioners are indiscriminately attempting to transfer variants of existing algorithms into hyperbolic geometry regardless of having strong motivations. Therefore, it is timely needed for a fair comparison and analysis on existing recommender system algorithm in hyperbolic space. It is also unknown that whether existing methods perform better in hyperbolic space compared against the original feature spaces. From dataset perspective, if hyperbolic geometry is regarded as a more suitable space for particular recommender scenarios, we are wondering whether hyperbolic space is versatile across different datasets, or it is only suitable for particular data sets. The fair latitudinal comparison are also missing in current existing works. So our work in KDD 2021 aims to fix this gap and provide a comprehensive analysis on hyperbolic space and the hyperbolic embedding for recommender systems. Our contribution are threefold. First, we provide a theoretical analysis and empirical results to validate our three hypotheses about the effectiveness of hyperbolic space. Second, we address the drawbacks of the hyperbolic space and give comments on what, when, and where to use hyperbolic space. Third, we propose a metric learning-based social recommender system, namely SCML, and it's a hyperbolic version of HSCML. And we validated our hypothesis on them, which we also show that hyperbolic space has state-of-the-art performance by comparing the two versions. Now let's look, let me introduce three hypotheses we proposed regarding the performance of hyperbolic space. Our empirical experiments are designed to evaluate the correctness of those hypotheses. First, we argue that distance models are more suitable for learning hyperbolic embedding than projection models, since the projection model optimizes the inner product and the distance methods optimize the distance. The distribution of embedding is different after convergence. For the projection models, the relation between nodes is mainly determined by the angle. The angles of positive pairs are small, and the angles of negative pairs are obtuse. However, for the distance models, the relation is only determined by the distance. The positive pairs are pushed close to each other, and the negative pairs are pushed away from each other. If we apply hyperbolic space to the projection models, one issue is that projection model usually regularize the norm of the embedding in a limited scale, which makes it impossible to push the embedding far away from the center. So in hyperbolic space, excuse me. So in hyperbolic space, the norm of the embedding will also be a limited scale, making it hard to make use of the outer product of the hyperbolic space while the capacity is the largest efficiently. Thus, reducing the expressiveness, however, the distance model do not have such limitations and can make use of this entire space. Embedding can be pushed arbitrarily from the origin as long as the precision allows. Another advantage of distance model is it has the ability to learn hierarchy information. Nodes on a circle have the same relation with the center node. So a group of leaf nodes will be likely to spread around the root nodes layer by layer in the form of concentric circles. As the number of the leaf nodes and the capacity of the hyperbolic space are all increasing exponentially, it's easier for distance model to learn low dimensional, no distortion hyperbolic embedding compared to the projection models. Therefore, distance models should be a better choice for learning hyperbolic embedding rather than projection models. Yeah, there are also, second one, we think the hyperbolic space is more powerful compared to Euclidean space when the density of the data set is small. Hyperbolic space is naturally capable of extracting the hierarchy information from data sets. It can use such hierarchy to help learn the node embedding more effectively. Therefore, it can have a relatively good performance, even though the density is low. However, it is quite difficult for Euclidean space to extract the hierarchy information. Instead, Euclidean space needs more user item pairs to help reach the comparable performance with hyperbolic space. That is to say, if the density of the dataset is small, then hyperbolic space is likely to outperform Euclidean space. But if the density is large, Euclidean space can have a comparable performance with hyperbolic space. The third one, we assume that the performance of hyperbolic space is better than Euclidean space when the latent size is small, but as the latent size increases, the performance of Euclidean space become comparable with the hyperbolic space. Now, let's look at the experiments results and evaluate our hypothesis on general item recommendations. We will show the results of social recommended scenario afterwards. First, we show that the influence of the density of the data sets. Let's take CML, that is collaborative metric learning, for an example. The picture in the first row are hit ratios and the NDCGs, movie length. And the picture in the second row are the automotive and the cell phone dataset in Amazon. Recall that the density of movie length is much larger than automotive and the cell phones. We may just focus on the pink and the red lines in those pictures, which represent that the hit ratios and the NDCG of the hyperbolic space and the Euclidean space respectively, when the latent size is 10. For movie length, the pink ones and the red ones are very close to each other, while for the automotive and the cell phones, the pink ones greatly outperform the red ones. If, in other words, hyperbolic space and Euclidean space have a very similar performance on movie length, however, hyperbolic space clearly outperforms Euclidean space on automotive and the cell phone datasets. This supports our hypothesis that hyperbolic space is more powerful compared to Euclidean space when the density of data set is small. Now, let's look at let's see how the latent size influences the performance of hyperbolic space. Again, we use the results of the CML as an example. Let's focus on the pictures in the second row. We can observe that the improvement of hyperbolic space over Euclidean space decreases as the latent size increases. When the latent size is 10, hyperbolic space significantly outperforms Euclidean space. However, as the latent space increases from 50 to 100, the performance of Euclidean space becomes comparable with hyperbolic space. This is consistent with our hypothesis that the performance of hyperbolic space is better than Euclidean space when the latent size is small, but as the latent size increases, the performance of Euclidean space becomes comparable with hyperbolic space. At last, let's see how hyperbolic performance perform in the distance model and the projection models. Here we show the results of two representative baseline methods, collaborative matrix learning and the MFBPR. Let's first look at the result of CML. So, from these pictures, we can observe the Euclidean space can never outperform hyperbolic space, and the hyperbolic space always has a larger or equal hit ratio and NDCG compared to Euclidean space. Recall that CML is a distance model, which suggests that the distance model is a good choice for learning hyperbolic embeddings. However, what about projection models? Does a hyperbolic space still outperform Euclidean space in projection models? To answer these questions, let's take a projection model as an example. For example, MFBPR, to quickly capture the idea, Let's look at the picture E here, which is a result of hitch ratio on automotive. The deep green line represents the results of Euclidean space when the latent size is 100, and the light green line represents the result of hyperbolic space when the latent size is also 100. We can observe that the deep green line is above the light green line. In other words, Euclidean space achieves a better heat ratio than hyperbolic space. This suggests that Euclidean space should be a better latent space than hyperbolic space for projection models. Therefore, our hypothesis regarding distance model and projection model is proved to be true, that distance models are more suitable for learning hyperbolic embedding than projection models. Yeah, so far we have discussed the findings on performance of graph-based recommender system in different embedding space. Apart from, we also summarize several key ground challenges in graph-based recommender systems. To name a few, for example, the heterogeneity nature, the dynamics of the system, as well as the as how to scale up the existing methods on complex graphs. Here, we would also like to introduce one of our research on solving the heterogeneity challenge in graph-based recommender systems. Okay, so yeah, so here's the example. The real-world information networks are always heterogeneous, which means different from the ideal scenario in simple graph that all the nodes and links in graph are single-tapped. The real-world information networks contain multiple objects and link taps. For example, here is an example showing Yelp networks where users, restaurants, as well as the associated attributes and the category information are linked together. Traditional methods on homogeneous network embedding cannot differentiate the semantics carried on the links. For example, a vertex U1 is close to both B2 and B3, but these relationships have very different semantics. B2 is a business visited by U1, while U3 is a friend of U1. To solve the problem of modeling semantic-specific relationships, previous attempts such as using metapaths or embedding like methods, etc., were proposed. However, these methods were using dot product to compute the proximity among nodes, which are not a metric-based distance and violates the crucial triangle inequality. For example, node A is close to node C and node B is also close to node C, which implies that node A is also close to node B. But existing works can only capture the local structure like both A and B are close to C, but they fail to capture the second order proximity, which is A and B are also very close. To solve the problem, in our KDD 18 paper, we propose the projected metric embedding, in short, PME, for heterogeneous information network embedding, which simultaneously preserves the first order proximity between nodes as well as the second order proximity. Sorry. Yeah. The proposed PME model introduced a relational specific projection embedding matrix inspired by the trans family, so that we model objects and relation in distinct spaces. For example, one shared object space and a multiple relational space, and performs proximity calculation while Euclidean distance in the corresponding relational space. Hence, it is possible that some objects are far away from each other in the object space, but are close to each other in the corresponding relational specific space. This allows for a greater extent of geometry, flexibility, and modeling capacity. The basic idea of PME is illustrated in this figure. For each observed link between a vertex Vi and Vg, vertices in the object space are first projected into the R relational space as a matrix multiplication projection with the operational matrix M. The relational specific projection can make vertices that actually hold the relation close with each other and also get far from those that do not hold the relations. As the number of unobserved links is huge in heterogeneous information networks, we adopt the bidirectional popularity biased negative sampling approach to optimize our PME model. Inspired by the good performance of the negative sampling-based optimization methods in networking embedding models such as LIME, PTE, and EOE. Yeah. Compared with the homogeneous networks, there are multiple relations in a heterogeneous network, and the distribution of the observed links with respect to the relations which are usually highly skewed, which poses a great challenge for the model optimization of PME. Take the YAP dataset, for example. More than half of the observed links are user links, friendships, and the second come with the user business links, which takes up more than 1/3. In contrast, business attributes and the business category only take a very small amount of the whole amount, respectively. During the model training, if we uniformly draw and observe the links and perform stochastic gradient descent on the drawn cases, just as done in the standard stochastic gradient descent algorithm, more than half of the chance the sampled observed links would belong to the user relationships, and it will lead a problem that the trained model may not be able to preserve the network structure of business attributes and business category relations. To address this challenge in a joint training as multiple relations, we propose a novel loss-aware adaptive sampling approach to draw observed links for model optimization. The basic idea is that the relations with a larger loss should have a higher probability to be sampled, as they need more training examples to correct the current model parameters. Extensive experiments have been conducted on a large-scale HIN data set, and the experimental results show the superiority of our proposed PME model in terms of prediction accuracy and scalability on the YAP dataset. If you are interested in our research, please find the details in our paper published in 2000 KDD80. And please also note that the comparison between different embedding spaces that works was published in KDD21. Interested audience are encouraged to refer to those two papers. Then here, I hand over to my PhD students, Ms. Yichong Li and Ms. Haoran Yang, for our recent progress on graph-based methods for explainability in recommender systems and using graph contrastive learning in recommender systems respectively. And thanks again for your attention.